Thanks a lot for the introduction, Anna. It's a great pleasure to be here. I've been here for 2 days now, and I've really enjoyed the lectures myself as well. There was a lot of super interesting talk covering very nice topics. And today I want to talk a little bit more from an applied point of view, how we're using machine learning at CERN, at the Large Hadron Collider, to improve the way in which we do physics. So I'm going to talk about a wide variety of topics. So one about data representation, why it matters, and how to find the best data representation for particle physics data sets. We're going to talk about different training paradigms, which also depends on the way in which we collect data at the Large Hadron Collider. And then I'm going to talk a little bit about my expertise, which is real-time inference, so edge inference, nanosecond latency domain, and anomaly detection. Okay, so at CERN, we have a very long history of big data and multivariate techniques. So most of you probably know that the World Wide Web was born at CERN because we had a lot of data and we had to share it with many different universities and researchers in a very short amount of time. And our data is also multidimensional, so we've been using multivariate techniques for very, very long. So this morning, I looked up the amount of papers we have in particle physics that include machine learning or neural or deep learning. And you can see here, as a function of time, the number of publications on deep learning in particle physics has grown exponentially. So just this year, we have 1,200 publications in particle physics where deep learning or machine learning is being used. What you can also see from this graph is that we've been using machine learning for quite a long time, since the 80s, where we really worked with boosted decision trees, multivariate analysis, etc. So even for the discovery of the Higgs boson, this would not have been possible without the use of machine learning techniques. We used 9 BDTs or something like that to make the sensitivity of the analysis higher, which meant that we could announce the discovery of the Higgs boson a year earlier than what would have been the case without the use of machine learning. So we depend on machine learning, and now we're in this deep learning era where we have more data, we have more powerful hardware, so we can really enhance the sensitivity of our searches. So what is the Large Hadron Collider? For those who don't know, it's a big particle accelerator where we accelerate protons up to almost the speed of light. They have very, very high energies, and we bring them to collide at the different collision points around this Large Hadron Collider ring, 27 kilometers. I work at the CMS detector. It looks like this. It's roughly 25 meters high. It's an enormous beast, and in the center, we collide protons at these very, very high energies. So this is what it looks like if you look kind of inside the detector. We have these big pipes of protons going in opposite direction. It's not one proton at the time. We have bunches of 10 to the 11 protons that are spaced by 25 nanoseconds at that speed, 7.5 meters. Every time we bring those bunches to cross, most of the stuff in those bunches is air. But roughly on average, we have 65 proton pairs that collide with one another. And the collisions occur, like I said, in the very center. When that happens, the energy of the incoming protons are converted into mass of new outgoing particles. So the protons vanish, new particles come out, and they shower through our detector, generating small signals in all of the sensors we have located around the collision points. And the reason we're doing this is to study the fundamental building blocks of matter, which we know are these. You see on one slide, we have 6 quarks, 6 leptons, force carriers, and the famous Higgs boson. And these particles are very, very different. So they span 9 orders of magnitude in mass, from the heaviest, the top quark, to the lightest, the neutrinos. And we need to be able to detect and accurately measure all of these particles, which are very, very different. And the way in which we do that is using a bunch of different types of detectors and detector materials. So here you have collisions occurring, and all these new particles radially spray out from the collision point and traverse the detector. And we know which particles were in that collision based on how they interact with the detector material. So if it's a muon, we know that it travels all the way through the detector without being stopped. So if you see signals here, we know a muon passed through. If it's a quark, we know it's charged. It leaves a signal in the inner tracker and dumps all of its energies in a hadronic calorimeter. So this is also how we discover new particles. That's how we discover the Higgs boson. So the Higgs boson lives for a very, very short time. It immediately decays into 2 C bosons, which then decay into leptons. So we look for signatures of a Higgs boson where we have these 4 lepton final states. Here you see a candidate event of that. Now, if we see something that looks like it could be from a Higgs boson, we keep trying to measure the energy and reconstruct the energy and momentum of those outgoing particles to infer the energy and momentum of the Higgs boson. So we took data for 3 years, and we kept measuring energy and momenta, energy momenta, until we have a peak around the Higgs mass. And that is how we discover the Higgs. It's by repeating the collisions, measuring how many times do we get something which is not on the Higgs mass, and how many times do we get something on the peak. And after 3 years of collisions, that's millions and billions of collisions, 10 events constituted our discovery of the Higgs boson and our announcement to the world that we discovered the Higgs boson. All right, so all of these things are described on this one slide. This is a quantum field theory. It's called the Standard Model of Particle Physics. It describes all of the force carriers, all of the particles, everything you're made of, how this room works, how my screen works. It describes almost everything. And before we start doing machine learning on quantum field theory objects, there are 2 things you have to think about. It's not vanilla cat and dog pictures. The 2 things that makes particle physics at CERN unique is, first and foremost, quantum fields. What that means is that every single collisions, I said, here's a picture of a Higgs boson, maybe a candidate Higgs boson. Every single time we collide protons, a Higgs is produced, a Higgs is not produced, and a Higgs is produced and not produced at the same time. So for a single collision, it's impossible to label that event. There's no label data, because in quantum mechanics, things can happen, not happen, and both things at the same time. The only thing we can do is do kind of a frequentist thing. We measure the same thing over and over and over again, and then we have a probability density function of the background process, then we have another probability density function of the Higgs, and then we do an hypothesis test. Is the data compatible with background only, or background plus signal? And these PDFs we basically get from Monte Carlo simulation, from our quantum field theory. So we have no labeled real data, doesn't exist. In order to account for that, we have extremely accurate Monte Carlo simulation. That Monte Carlo simulation goes from a handful of particles where you have Higgs is produced, decays to 2 Z bosons, decays to 4 leptons, a handful of particles. And it simulates how those particles hadronize, they bind to become other particles, spray and shower through the detector until it leaves billions of hits in detector channels. So our simulation covers going from 10 particles to millions, billions of channels, and 20 orders of magnitude in length, from 10 to the minus 18 meters, roughly the size of the Higgs, to 100 meters in length scale. We have accurate simulation of that. That defines the 2 data sets we have. We have real collision data. We currently have 40 quadrillion collisions recorded at the LHC with more than 400 picobytes on tape and 300 picobytes on disk. We actually produce 400 exobytes each year, but we're forced to get rid of. Please go ahead.
So in the previous slide, you showed the modeling aspect, right? So when you model this, do you also, do you also model the imperfections of the detectors themselves? Because
yes.
Those are
we have to model every single aspect of particle interaction with material, including real detector material, all the cables in between, dead material, everything. And this is extremely compute heavy. Okay, so we have this enormous amount of data, and in order to make accurate PDFs that we compare that data to, we need enormous amount of simulations. We have trillions and trillions of simulated events. These 2 facts, no labels on real data, doesn't exist, we have a lot of simulation, defines how we can train machine learning algorithms at the Large Hadron Collider. Fully supervised training requiring truth labels, we can only do on simulation. We can never do a supervised training on real data. If you want to use real data, we can only do weakly supervised training where we have unpure labels that we derive from the data itself, or self-supervised or unsupervised training where we have no labels and it's completely data-driven. All right, so one of the first tasks that we kind of want to do to be better in analyzing data at the Large Hadron Collider is to basically identify which particles were made in each collision. And if we take these quarks, these are kind of interesting because once they're produced, they immediately decay to other particles, generating a spray of outgoing particles. So we have a spray of particles stemming from one of these guys, and they pass through an inhomogeneous detector. And what we want to figure out is basically which quark generated this jet. Now, a problem is, how do we take something like this and force it into something like this, where you have basically some regular input, an array, a 2D grid picture? So we tried a lot of different data representations for the data that we have at CERN. The first one we tried was images, where each of the pixel intensities corresponds to an energy. But the problem with that for us was that they're really, really sparse. So you have sparse convolutional neural networks, but they didn't give us the best performance possible. So this representation was not great for us. Also, we have inhomogeneous detectors. They have a lot of sensor in one direction, fewer sensor in the other, big sensors there, small sensors there. So we kind of have to move on from that approach. We try to model our data as a sequence, so we could take advantage of RNNs, for instance. But then we have the problem of permutation invariance. So whereas in our spray of particles, it doesn't really matter which order you take those particles in. They should be permutation invariant. So that didn't work. And where we are currently is treating our data as point clouds. So once we want to have a full picture of a collision event, we treat them basically as points in momentum space. An inspiration we got from LiDARs and self-driving cars, where you basically have points in position space as your input data, unordered, unsorted. And we now have these points in momentum space. So for us, point clouds have turned out to be the best representation of our data.
Yeah, I believe that we have a question.
So does that mean that every point is basically one input rather than all the points from the same experiment being one input, or?
All of the points which are particles in the detector, it's one node, basically. One point with some features. And they don't have to be homogeneous. They can be heterogeneous and have different features depending on which detector point you're in.
Then actually there was on the other side first.
Sorry.
So my question is, you said that the first approach, for example, was not promising, but did you have any other approach to compare it with, or was it like a...
At that point, we just realized that, okay, we've reached a cap of accuracy here, and then we experimented with new algorithms that were coming out in the literature, and then we saw, okay, we can overcome this if we do this, we can overcome this if we do this. So we have a lot of benchmarking data sets that we really can compare one to the other. And this is like really for us, that's in science too. You really have to understand your data and all the symmetries and invariances that are in the data when you start thinking about architectures and data representation. It's crucial. Also in chemistry and biology, I guess, the same.
Okay, and we had one last question here.
So when you say point cloud, does each point also have like a probability associated to it to account for the detector uncertainties or detector, error bounds on how you measure?
Yeah, they can have, the vector of features can be whatever, and it depends a little bit which problem we're trying to solve. But often we add like smearing factors, like we're uncertain of this energy by X sigma, etc. So we try to include that as well. Go ahead.
And what are the positional embeddings of the point cloud? Is it a Cartesian grid or is it Minkowski space? What is it?
It depends. We've tried either having basically no, just PT eta phi space, which is kind of just spherical coordinates. We've tried that. We've also tried the Minkowski metric to really infuse physics Lorentz symmetries into the networks. And we see a lot of promising results when we really try to incorporate the formalism of the standard model basically into
I guess it's state of the art, right?
Themselves.
The Lorentz net?
Lorentz net, exactly. That does exactly that.
Okay, the questions are coming in. One here.
So if you said that you are using Minkowski metric, does it mean that you also encoded some relation between points? And in the previous case, where you weren't using any metrics, then the data was just like lacking any spatial information?
Then they had like spatial information in spherical coordinates. That's like kind of how we've started out, and what we're often using a lot of times, because we just wrap this thing kind of out and around, and then you have a distance between vectors. So we use just normal Euclidean vectors or spherical coordinates. And then once we use the Minkowski space, we then include a time coordinate and use that for the positional encodings. So when we're not doing kind of Minkowski matrix stuff, it's really just position coordinates and spherical coordinates around this thing here.
I just want to know that you said that Higgs particle is just vanishes very soon. And you should record for a very long time with different experiments so you can find it. So is it means that you cannot detect it because it's just go fast to the other thing? So you 10 of the detection of over 11 years means that just you detect 10 of them, or it means that you should gather data enough that the other particles are there, then you can say that, okay, if these other particles are that much there, it should be the Higgs particles.
No human being has ever seen a Higgs boson. We only see what it decays into. It's like in a quantum field theory, things just become kind of a wave on a field. It becomes an excitation that's super short-lived. So we only see what it decays into. You've never seen a Higgs boson. We only see the decay products. And we know from our standard model mathematics formalism that if there was no Higgs boson, the invariant masses of all of these particles would be smoothly falling with energy. It becomes less and less probable to produce leptons with that energy. If there's a Higgs boson, there's an increased probability of having higher energy leptons. So it becomes like a resonance on the Higgs mass. But no one has seen a Higgs boson. We never detect the Higgs boson, only the decay products. It's the same for a lot of things also. Same for the W boson, for the C boson. We never see them, what they decay into.
Okay, so if I understood correctly, like each of the data points that you captured is composed out of each of the particles that get emitted after the collision, right? And how important is like the exact position versus, I don't know, the energy of the particles?
So we get, oftentimes we also get the energy itself from the position. So we also measure the particles when they go through, if they're charged, we have a huge magnet in CMS, so that when charged particles pass through the detector, they're bent. And when they're bent from the curvature, we can figure out their momentum. So we need their position to get the momentum very, very accurate. And then we also can get their energy from the calorimeter deposit themselves. There is, in our theory, since we are colliding things head on, the Z component basically should be 0 because momentum is conserved. So we don't really care so much about momentum in the Z direction, but in PX and PY, we care about the momentum. So therefore we have a rotational symmetry in phi, spherical coordinate phi. We don't care where things are in phi, doesn't matter, but we care where they are in eta. So it depends a little bit, but we need high resolution for eta and for position in terms of a position vector.
Okay, so discretizing the space somehow isn't an option for you basically in this case? You need to have a continuity along the dimensions.
Well, we are kind of discretizing the space just by the detector itself. So it isn't continuous. So currently we're anyways combining, when you remember the slice, I showed like all these different types of detector material. They have different sizes, they interact differently. So ideally, we'd also want to account for like what's the size and resolution of those detectors, where are they, and the same for the next one. It's completely inhomogeneous and it's not continual, but we approximate it as continual, which is not true.
Thank you.
Thanks. Okay, so we have our point cloud, and that allowed us to also take advantage of what was kind of new and nice at the time. So the particles in a jet become nodes in a graph with edges that connect them. So each node has features. They can be heterogeneous, they can be homogeneous, and they have some relation to one another. Now, in astronomy, I think these connections can make a lot of sense because you have gravitational potential, some planets pull on other potentials. Quantum field theory, it's not so obvious how the particles are connected. So one can discuss how relevant like information you can put in the edges. But yeah, then basically we could use graph neural networks on these guys, embedding the features of the nodes, having message passing or edge features or MLPs as well, that we then pass through some invariant operation, ensuring that it's permutation invariant, and then classifying particles as basically up or down. You don't need to read all these names, it's just a list of our state-of-the-art particle identification algorithms, our graph nets acting on point clouds. So graph neural networks were great for us. We could really kind of outperform the previous generation of architectures we had. And then adding attention really elevated it for us another step up. So I really, really like, I mean, you're all computer scientists. This is like your probably bread and butter, but I really, really like this example of self-attention. So adding self-attention for us allows all the particles to kind of interact with each other and figure out which other particles matter to it. Like, we're close to each other, this is important. And I think this is kind of nice, like if you see the intention waits for the word it in this sentence, the animal didn't cross the street because it was too tired. You want the network to kind of see the full sentence and say, for the word it, it should pay a lot of attention to animal in this case and less to the others. Whereas if you have a sentence, the animal didn't cross the street because it was too wide, it now should give a high degree of attention to the word street. So we've added a lot of self-attention to our neural networks as well, where we have the basic attention mechanism where you have a particles and its neighbors. You weigh the sum over all of these input particles and you see how related each particles are to all of the other particles around it. And then you normalize it, map it to 0 or 1. So vanilla attention. So now we have this weighted importance between each pair of particles, which completely determines the relationships between all of the particles that we have in our point cloud. And then we have these several attention layers for multi-head attention to really point out different important features inside the jet itself. And here you can see an example of 2 different jets. These are the attention weights, where you see, for instance, for a light quark, a jet from a light quark only has 1 quark inside, so it only cares what's in the center. Whereas in a Z boson, you have 2 quarks inside, so it already knows, the particles that are here matters more. If it has 2 quarks, I'm a W. So it's learned this substructure all by itself. So that was super useful for us. Okay, so graph neural networks, self-attention has been really, really powerful. One more thing for us is that we can't afford a lot of compute. So if there are things we can get rid of, we want to get rid of it. And oftentimes for these classifications, we have point clouds, we have a set of information. Not always do we need information from the nodes. So often in high energy physics, we only need permutation and variance. We don't care so much about how the particles talk to one another. So also deep sets are for us a really, really good architecture where each input is transformed by some network phi, and you sum up the results and you apply a final neural network row in the end, which has the benefit of a linear scaling in computation time, which for us is beneficial. Now, every machine learning person hates when I say, okay, yeah, then we train our great graph neural networks with attention to do particle identification, and then I test it on a completely different data set. Because remember, I train on simulation, and I test on data. And they're like, no, you did all this fancy stuff, and then your test set is just a completely different data set altogether. So, for instance, in simulation, you can have, just think of this as some features you look on in simulation versus some features you look on in data. They are vastly different. And if we train on simulation and then test on data, obviously this is completely suboptimal and there's a lot of uncertainty we need to account for. But we don't have labels in data, so what are we going to do? So that brings us to the weakly supervised regime, where we use unpure labels that we derive from data itself. So how do we do that? So you already saw this plot, right? You saw there is some observable, doesn't matter what it is, and then it peaks at one place for the signal and not in other places. So what you can show is that if you have mixed samples where you have, for instance, mostly background here, signal plus background here, mostly background here, the best classifier to discriminate this region from these regions is also the best classifier to discriminate the red from the green. That means that one thing you can do if you want to train a classifier, data-driven, you can simply label data from here as signal and label data from here as background and then train a normal classifier. So that's a shortcut we often use if we can very, very, very well define these different regions. So another cool thing we do is hybrid approaches where we use data and simulation. So I don't know if you've heard about neutrinos. They're this really whimsical particle. There's like 300 of them traveling through your hand every second. And these neutrinos can change their flavor as they fly. They can start out as electron neutrinos and then they become muon neutrinos. So for instance, a muon neutrino enters Earth here, passes through on the other side. It's a different type of neutrino. And we obviously want to measure this because it's input to the standard model of particle physics. So we do the same. We make a beam of muon neutrinos in Chicago and we shoot them 800 kilometers to Minnesota and we see if they change their flavor. Now, in this detector, where we're going to observe if these mu neutrinos became mu-e neutrinos, it's very unlikely that they change their flavor. And we really want to make sure that we can detect the ones that are nu-e and not the ones that are nu-nu. But most of the data we have are these type of neutrinos. So when we detect these neutrinos, what we detect is that they decay into something with a muon inside. And the other one that's nu-e decays into something with an electron inside. So we design a CNN and we want to detect the cases where we have electron neutrino. So one thing we can do is that we can use the real data we have, which is mostly the muon neutrinos, and then we remove this muon and then we put an electron in there. So we have the data, but we've just swapped this particle. And then we can train a classifier. So here you can see what we see in real data. Then we remove this muon, and then we put an electron in from simulation. So we create these hybrid data sets. It's also something we do a lot. All right, so this is kind of an overview of where we stand on particle identification at CERN. So here you can see as a function of the number of parameters and the performance as a function of number of parameters. We started here pre-deep learning with these classical variables. Then we did CNNs. The performance got a little bit better. The size got also bigger. Message passing graphs, the performance got even better. Transformers, adding attention, really powerful. And now we are here where we have these physics-informed networks that really respect Lorentz group symmetries. They allow us to have smaller networks because they respect symmetries, and we infuse physics in there. So for us, the latest trend is really put formalism in there and in physics knowledge. Okay, now over to machine learning for higher efficiency. This was machine learning for higher sensitivity. Now we're going to talk about compute, which I think is a lot of fun. So often in these type of things, when you have machine learning school for science, we talk about like these huge, super impressive models like AlphaFold. And here you have Oriol. He was at CERN last year presenting AlphaFold to us, these fantastic algorithms that can predict how a sequence of amino acids will fold. And the way they fold completely determines their function. Pre-AlphaFold, we knew 17% of the 20,000 proteins, the structure of them in our body. Post-AlphaFold, we know 98%. So AlphaFold, big, big, big deal. Also, when we talk about machine learning with our friends, there's large language models. They're so amazing. They can do fantastic things. They can figure out humor in images. They can reason from graphs. They're amazing. So what does this have to do with machine learning for efficiency? Well, GPT-3, we know, was 175 billion parameters. GPT-4, we don't know if it's a huge model, 3 orders of magnitude larger, or if it's just a mixture of experts around 200 billion parameters each. But the point is that they're huge. This means that not a lot of people can train or run inference on these models. So GPT-3 was trained on a supercomputer with 300,000 CPU cores, 10,000 GPUs, all connected with 400 gigabits per second networking, trained for several weeks on a 25-kilometer high book of text. When we run inference, we don't even know where the thing is running, but judging from just the sheer size of it, it must be at least 5 to 10, 20 powerful GPUs. So something that we see in general in deep learning is that you increase compute, you increase the data set size, you increase the number of parameters, your loss goes down. This seems to be a generic scaling law. So that's, I mean, it's good we can get the loss down, but this means it's at the cost of compute, hardware, data. This is in contrast with the way that hardware scales. So here you can see as a function of the year, the number of parameters in computer vision models and for transformer models in reds, where transformer models grows by roughly a factor of 240 every 2 years. Whereas the hardware memory itself only grows by a factor of 2 or so each year. So judging from just the size of GPT-3, you would need roughly 5 of these $20,000 GPUs just to put the model on there. Meaning that a lot of people can't even run these models. What does it have to do with CERN? Well, whereas for GPT, you can run inference on these 11 interconnected GPUs, and you can tolerate a latency of 4 seconds, something like that. That's how long you have to wait for an answer. At CERN, we have to do inference on one tiny, tiny chip within a billionth of a second. Actually, if you look at the streaming data rate, how much data goes through our system versus the latency requirement, how fast we have to go to process that data, we're at this extreme edge of the inference spectrum compared to Google Cloud or Netflix. We also produce way more data, more than an exabyte of data per year in comparison to both of these. So where is all this data? Yes.
Where is the latency requirement coming from? Like, why do you have to do it so fast? I thought you just take the data and then later offline identify everything else.
I will show you in roughly 30 seconds. So where is all this data coming from? Well, it's coming from here. We have billions of sensors. So we have 10 billion collisions per second, generating up to 10 petabytes of data every single second. Now, luckily for us, we already talked about 3 years of data taking 10 events was the Higgs boson. So just listen, don't look at this next plot too carefully, just listen to my voice. So up here is the probability of producing anything at the Large Hadron Collider. Down here is the probability, and it's quantum mechanics, quantum field theory is all about probabilities. Down here is the probability of producing a Higgs. So I need to produce a lot of collisions to enhance my probability of producing a Higgs. So that means even if I could save all of these collisions, I wouldn't even want to, because most of them I don't care about. I want this guy down here. So what we do is that we have a real-time event filtering system in place. So here you can see my office from a nicer point of view. Here is the Large Hadron Collider. It's located 50 to 100 meters underground. This is where I work. Here is where the collisions happen. So we have this 10 petabytes of data per second. What happens next is, so you saw there was the bunches of protons crossing each other every 25 nanosecond. So a collision happens. What happens next is that I buffer that data in pipelines inside my detector for 12 microseconds. When that data is buffered, I take a small subset of that data and I send it through high-speed optical links to a radiation-shielded cavern right next to the experiment. It's radiation shielded because here is heavy radiation. No one is allowed inside there when we're colliding data. If someone enters the door to go in here, the whole accelerator shuts down. So a lot of radiation. It's also located down here because speed of light is a limitation for us. Data transfer takes time, so that cable length is what we can afford. Here we have 1,000 FPGAs that decide which event to keep and which to reject within 12 microseconds. And we need to reject over 98% of the collision events. So I looked at the event and I see, is there a Higgs in there? Is there not a Higgs in there? Is there something else interesting? Then I say, I accept this event. I send one signal back to the detector, 1. I reject the event. I send one signal back to the detector, 0. If that signal is 0, I flush the buffer. I get rid of all the data. I will never see it again. The data is lost. If I send a 1 back to the detector, I trigger an immediate readout of the full detector, sending the data upstream at 750,000 per second, roughly at a rate of terabits per second, to the high-level trigger. High-level trigger located right above the detector, not further. Speed of light is a limitation. It's right above the detector, and only at this point have I read out the detector. It's still too much data, so here I have 300 to 400 milliseconds to reject further 99% of the data coming from here. I do this on CPUs and GPUs because I have heaps of time. I have 300 milliseconds. So only after accept from the high-level trigger do I send the data out at a rate of 7.5 kilohertz, gigabits per second of data, to our compute center located at CERN, where we do a full reconstruction and storage of the events on tape and on disk. Like I said, we currently have 400 picobytes on tape and 300 picobytes on disk. All right, so I just got rid of almost all of my data before any human looked at it. And if I'm going to discover the Higgs boson with 10 events, I'm going to have to make sure that I select the right 0.02%. So the algorithms need to be really fast and really accurate. We already discovered the Higgs boson, so why am I even giving this talk? Well, if we want to find new physics, we know the standard model is missing something.
So I wanted to ask, when you do one collision, you get some data, like a part of it, and then based on the part of it, you decide if the rest is interesting. Can you maybe explain a bit more how this part of the data can tell you if the rest contains the information you're searching for?
We try to make the most representative subset of the data that we can. So we compress the full detector basically into fewer bits of information. So it's not like we're just taking out a region of the detector, we're looking at the whole thing, but we're really just taking the big picture. So it's a lot of compression going on before it leaves the detector.
Another question?
Sorry, I'm not sure I understood why there is a time limitation as to why you need to decide it so quickly.
So it's because every 25 nanoseconds, there's a new bunch of protons coming through. And I can only pipeline for so much, buffer the data for so much, because I'm inside the detector itself. If I would add more buffering pipelines, more material, less detector material. So it's like this fine balance of how long can I buffer the data. I mean, ideally, we would just read out everything, but that would require so much cabling and so much power that we need to give to the detector that the detector would have no detector material anymore. It would just be cables, the whole thing. So we really can't read out all the data. And there's new collisions coming always.
Would it be, I don't know if it's detrimental, but would it be possible to delay the next collision to have a little bit more time to read the data?
We actually can't because we need to generate so much data. So it's really like this is like we've made it as tight as we can, with as many protons as we can, as much as our system can tolerate, because we need so much statistics. Since it's a game of statistics, we want them to come as close as possible. We have had them, like we do often start off the detector with a bit more spacing, but then our goal is to have them spaced as much as possible.
Thank you.
And I mean, in order to have them, we have a very specific frequency because we always need to bend these particles, and we use magnets to do that. And they are really, really fine-tuned. So it's very, like these timing constraints and where the particles are is crucial for basically how the magnets should work, how much we should bend them so we can bend them at the right time, etc. So timing is super strict.
Another question there.
Can you give us a bit of details about the compression? Like
Yeah, I'm going to talk about that later on from the machine learning point of view.
Okay,
yeah.
Thanks.
And one here.
So just basic understanding for me, so you do like 10 billion collisions and you only see in 10 collisions traces of the Higgs boson. Is this because it only gets to be, like you're only measuring the follow-up products of the Higgs boson. So do you only measure them, are they only generated 10 times, one in a billion or really?
According to quantum field theory, that is how often it is produced, basically. If you collide protons with this energy, you can only produce a Higgs X many times. It comes from the quantum field theory of the Standard Model.
Okay, so you kind of get it every time, so it's not even that the sensors are like noisy.
No, it's just physics, just reality, basically. Like you have to do it over and over and over again, and it's so improbable you can do it. It's really quantum mechanics and probabilities. And some things are very unlikely to be produced.
And if it happens, you have such exact sensors that you can measure it every time?
No.
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 but close to every.
Because we have to also get rid of the background. So we have so much data produced. So when we discovered the Higgs, we had, I think, under the Higgs peak, we had 5 background events and 10 signal events. In order to go from 1 billion events to 5 and 10, we have to do a lot of cuts and selections in advance to really narrow in on the Higgs. So we do a lot of also focusing in on that region. So we discard a lot of the data through selection cuts. Like we require the electron to have this energy. We require it to be in a clean region of the detector. And then we also cut away a lot of signal acceptance. So it's both things. One is our selections that reduces the acceptance, and one is quantum mechanics. So unprobable, and we need to put tight constraint, like only select very high quality Higgs candidate collisions.
Ah, okay. So of 1 billion where the Higgs boson shows, how many can you really like then process later on, because of like the noise and stuff?
It really depends. I mean, we only produce. Yeah, that really depends on which decay channel you're looking at. So the Higgs cannot just end up in a lepton final state. It can be photons, can be other particles. So it really depends which region you're looking at. But it's really just like order of 10 out of maybe, yeah, I don't know. Yeah, I can't really say. It really depends on the channel.
Okay, thank you.
Yeah, but it's really mostly that it's just so seldomly produced. That's like the bulk of it. And then we try to keep as many of them as possible.
So since you mentioned how much you have to cut and select, do you also use tools like experiment design and such, like optimally design which experiments or where to look at to get the most high probability of seeing a Higgs boson or some other particle?
Not for like the experiment themselves, but we have some like detector, like machine learning for detector design. So really figuring out what would be the best positioning of sensors and material to get the optimal. Yeah, so we have like a lot of new projects looking at that, but people are super scared. It's like, no, that algorithm is not going to design our detector. All right, so if we're going to detect new physics, that's produced 1 in a trillion, if at all. So in the future, we're going to make our problem even harder. We're going to upgrade the Large Hadron Collider in 2 years to something called high luminosity LHC. LHC is gone, we have the high luminosity LHC. Then we will have a factor of 10 more data with a factor of 3 more collisions per second. And the way we're going to do that is having 2 times more protons per bunch and to squeeze the beams more where they collide so that the overlap between protons is higher. So that's great. We have more data. We're going to find new physics in no time. The problem is just that the event complexity will increase enormously. So here is what happens when we have roughly 60 proton pairs colliding every bunch crossing. And we have to detangle all of these lines, which of these lines were made by which particle. And we don't even see the lines, right? We just see sensors, bleep, bleep, bleep. We have to track and figure out which hits belongs to the same line. In the future, we're going to have 200 pairs on average colliding. So it's way harder to detangle. So we even have to upgrade our detectors to really be able to detangle this. So we're buying new calorimeters. Our current calorimeter with 85,000 readout channels will in the future have 6 million. So we have more collisions and we have more readout channels. And unfortunately, since we're kind of a non-profit organization, our computing budget is basically flat. So as a function of the year, this is the number of compute we're going to need. The gray is what we can afford. The blue is the reality with more data and more complex detector. So we need a lot of innovation in the next couple of years and new techniques to even maintain what we're doing today. So that's why we are highly involved in R&D to use machine learning to become faster, better, and to do more. And what I'm working on is fast inference on specialized hardware. So how can we do better at the HLT, so GPU inference, latency milliseconds, FPGA inference where you have microseconds, and inside the detector itself where you have nanoseconds to do an inference. So the constraints of these algorithms here is that they have to be very low latency. Every 25 nanoseconds, you have new data ticking in. On a single chip, you're also running several algorithms in parallel, so you can't take up the full chip. Thirdly, they have to be really power efficient. So if you're inside the detector, it's often cooled, so you're limited to milliwatts. And if you're in the level 1 FPGA farm, you're underground, cooling and power is a major challenge for us. So the first question, was it you who asked? I can't remember. You. How do we go from petabytes of data generated to terabits that's read out? And we do that by taking a representative subset of the data. So for instance, we bought this very expensive new calorimeter with 6.5 million readout channels. So that's 50 layers so that we can see the full particle traversing the detector. Unfortunately, we cannot read out all of these channels fast enough to trigger on them. So why did we purchase the thing in the first place? So the thing we have to do is that inside the detector itself, on the detector sensors, we have ASICs. And they have the job of reducing and transmitting the data. So you have one data stream sent out to the level 1, one data stream sending the data out of the detector. So this ASIC sends the data basically out of the detector. And this whole thing is in high radiation, so the ASIC needs to be radiation tolerant. The whole thing is cooled to minus 30 degrees, so very low power, anything inside the detector. And you have 1.5 microseconds to do this compression. So here, what we're doing is using variational autoencoders to basically take the input data, learn to compress it, decompress it again. So you have this lower dimensional embedded space. Then we want to put these deep neural networks inside the detector on ASICs. We transmit the encoded data through the high-speed optical links to the level 1 trigger, where we either decompress it again or just work on the latent space as it is. Very cool. These can run with 75 milliwatts or so using techniques we've developed. We've triplicated all the weights and the biases, because sometimes due to radiation you have a bit flip. So all the weights, you have 3 of them. And the weights are reprogrammable because the conditions in the detector change. All right, so the level 1 trigger. This is a super cool system. Here we have 1,000 FPGAs on custom boards. Here you see the high-speed optical links plugging into the boards. All these FPGAs works on different part of the problem. So some process the data from here, 200 FPGAs here. You have 400 FPGAs doing calorimetry, etc. It passes the data on before it gives one output, 0 or 1, basically. Some algorithms, so none of the algorithms can take 12.5 microseconds because they need to feed downstream. So this needs to be done in 5 microseconds, etc. Why are we using FPGAs at the LHC, and what are FPGAs? Why aren't we using GPUs or CPUs? The most important thing is that you have high resource parallelism. So the FPGAs you can program very, very low level. So you can either work on different parts of a problem simultaneously, and even different data simultaneously. So we get one collision in. Before we're done with that one, we take the next one and the next one. So we have up to 10 collision data inside the FPGA all at once. Secondly, they're really power efficient, up to 10 times more power efficient than GPUs. And even with these FPGAs, they dissipate a heat of 7 watts per squared centimeter, 100 meters underground, while processing 5% of the total internet traffic. Again, 100 meters underground. They're also, and most importantly, latency deterministic. Every time you run a program on your CPU or GPU, sometimes it's 1 nanosecond faster, sometimes it's 1 nanosecond slower. We cannot afford that. We need to be on the clock because the next data is coming in. So this is an FPGA. An FPGA was used to kind of program as ASICs. So there's a bunch of resources, and you can connect them as you want. The function isn't soldered. It's basically something you can change. It has memory. It has logic cells that can do arbitrary functions and serve as a small memory. Flip-flops register the data with the clock pulse. So you do like A plus B, and then the flip-flop holds on to the data until exactly the right nanosecond to let it go again. And then you have DSPs, which are specialized units for multiplication. Now, if you want to put any sort of code on an FPGA, you usually write some C++ code with some constraints or directives, like how parallel should this be, how pipeline should it be. And then you pass this code to a compiler that depends on which FPGA you have. I have Xilinx FPGA, so I use Vitis or Vivado HLS. This then compiles that code into a hardware description language that you can then synthesize to a firmware block. The problem is, if you're going to write machine learning algorithms that are extremely fast, so nanoseconds, and very efficient, that requires a lot of expertise. So we have to deploy stuff on FPGAs that are really busy with very small target latencies. And translating neural networks into efficient firmware blocks isn't well served by the industry. You've seen the plot, right, of like latency and throughput constraints. We're quite unique in the position we're in. So what we've designed is 2 libraries, HLS4ML and Conifer, that can take your favorite machine learning algorithm in, all Python-based, and translate it, write that C++ code for you that you can then put on an FPGA or design an ASIC. So the way this works is that you start with some model, caveat is that that model needs to have been efficiently designed, so quantized or pruned. We'll talk about that afterwards. You pass it to us. We write the C++ code for you. So we first convert the model to some internal representation. We write the project for you. You can emulate the C++ code that it wrote and then make the firmware that you can either use as a co-processing kernel. So you plug an FPGA into your computer to accelerate inference. Some of the inference runs on the FPGA. You integrate it in a full FPGA design, or you can print an ASIC. Here you can see an example of how cool and nice this is. Yeah.
I have a few questions. So first is, so you mentioned that you're using ASICs at the level of the detector itself, whereas FPGA is at L1. Why this? Why not ASICs all the way through?
Because they have to be reprogrammed frequently, and we can't afford to print 5 ASICs that do that, 2 ASICs that do that, 3 ASICs that do that. And then, yeah, as soon as conditions change, or for instance, we buy a new detector, you're going to have to change what those FPGAs are going to have to do in terms of reconstruction. And the reason, yeah, and obviously the ASICs we use because they're radiation hard and fast.
Okay, and for the FPGA development, do you guys also look at things like verification? Like, do you verify the whole design? Do you use things like UVM and system Verilog to verify whole things? I'm asking because you mentioned HLS, and
yeah.
I don't know if that allows for complete verification and such.
No, with the HLS part, we can only validate basically the C synthesis. So you can write the full emulation of the C synthesis, where you can check the accuracy and check that the weights are implemented accurately. But then once you're at the Verilog or VHDL level, then we use traditional tools. It's not part of the Python package.
So if you have like a neural network, there's a lot of parallelized stuff that's running.
Yeah.
If you then convert it into C++, is it still parallel or not?
We write the layers to be maximally parallel. That's the design we come with. So our job is basically how can we translate that into basically FPGA code. So unroll the full thing, make it everything parallel. That's something we've customly implemented so to ensure that max parallelism, lowest latency is achievable. Okay. So that's part of our design. But all this is done manually, yeah? I mean, we write the loop unrollings. Yeah.
Okay. So I probably got that wrong, but did you say that you reprogram the weights on the ASICs?
Yeah, we have this IC2 protocol, so you can change the weights without having them wired.
Oh, wow.
It's quite cool.
Thank you.
Yeah.
Okay, so back to compression problem.
Yeah.
What is the output of the network that you get? Is it like some sort of probability?
Just 16 ReLU activated nodes.
Okay.
That's it.
And what do you get of it? What is the signal that you get out?
The signal is just the same sensor hits. It's all the voltages and all of the cells that we decompress it back into. So we have sensor, like energies per sensor in, energies per sensor out. If we do the decoding again.
Okay,
yeah.
Thank you.
Okay, yeah, so here's the piece of code. You have a CNN for MNIST classification. You load the model. You kind of configure it through HLS for ML. You can compile the C++ code and run a full emulation of the code and then build the firmware, all in kind of nice, easy steps. And here you can see the design on an FPGA. Each color belongs to each layer. These are all the resources, and the wires you can't really see. Two things I want to point out. One thing is that with us, our solution is fully on chip. You can store the weights on off-chip memory. Again, the latency, sending data back and forth, we can't tolerate it. So the whole thing needs to fit on the chip. Secondly, look how full this guy is. This is quite a tiny neural network, and you're already filling up the full FPGA, so that's a problem. So actually, the number of multiplication is your huge, huge bottleneck. If you have some small MLP, 16 inputs, 5 outputs, you're already at 4,000 synapses. And high-end FPGAs have 5,000 or so units for multiplication. So you're already filling the thing. Yeah.
Can you go back to the previous slide and explain a bit about the color coding between this FPGA diagram and the
Here it's just the layers. So green is green, so the softmax takes up a lot of space.
But then why does softmax take up a lot of space? Because convolution is essentially a big matrix multiplication compared to softmax, which is...
For us, it's just that the softmax is pre-computed and stored as a lookup table on memory. We can't do the compute, it takes too long. We can't compute the softmax on the chip, then we've lost all of our time, basically. Most of our algorithms are 50 nanoseconds. So you pre-compute it, and all it has to do is take an input and read the output. So you have to store a lot of output values for a lot of input values.
Okay, got it.
Yeah.
How do you deal with, I mean, in what precision, in what numerical precision do you operate? Do you
I'm
use
going to
mixed
also
precision?
mention that in 5 seconds, yeah. I'm happy you asked, because it gives me the chance of saying I'll mention that in 5 seconds. All right. Okay, yeah, exactly. These guys pre-computed, stored in memory, multiplication on DSPs, addition goes on logic side. So, ideally, this, reality, this. That's also where numerical precision comes in. So we really can't afford to do grand things. We really have to fit on the chip itself. So efficient inference for edge compute, whether this is your AirPods, an FPGA, smartwatch, or for a self-driving car, every time you deploy a deep neural network on the edge, you need to make it efficient, and there's 3 main ways to do that. One is quantization. You really need floating point 32 precision. Second one is pruning, so remove insignificant weights or synapses. Parallelize if you want low latency, so anything that should be done in parallel. And you can also look at doing something like knowledge distillation, where you train a big network, distill the knowledge into a small, and deploy that one. So most important is quantization, numerical precision. So obviously, every time you train, you most likely train in floating point 32, so you have a very large dynamic range and very fine granularity. Floating point 32 is memory intensive, and doing floating point 32 arithmetic is also latency expensive. So let's go again to GPT. GPT was deployed, as far as I know, in floating point 16, trained in floating point 32. So the floating point 32 version would use 700 gigabits bytes of memory, which is an order of magnitude larger than a single GPU, whereas the deploy-ready GPT at floating point 16 uses 350 gigabytes of memory. Now, on the FPGAs, we can really custom things. We're not like in GPU world where you have int8 and int16. You can do any precision that you want on the hardware, and we use fixed point arithmetic, so fixed number of digits before and after the decimal points. Here you use exactly the same weights in 4-bit precision, so you now have all the numbers in little buckets, the dynamical range is smaller, the granularity is lower. If you're going to do this post-training, it's lossy by definition, right? So you have this fine granularity, and now you put it in buckets. The tinier the buckets, the bigger the buckets, the accuracy goes down. At some point, you might as well do a coin toss. Your algorithm is useless. So is there a better way you can do this? Yes, you can do something called quantization-aware training, which is kind of a software-hardware co-design process, where in the forward pass, you already put the weights and biases in buckets. You tell the algorithm what the precision of your numbers are. Then on the back propagation, you do everything in floating point. Also, this quantization operation is non-differentiable, so you use the identity function to approximate it. And you do the normal training loop. So the weights will adapt to the precision they will have on the hardware. And we work together with Google on making a streamlined approach where you can do quantization-aware training and put those models on an FPGA. Here's how simple you can train such a quantized neural network. In Keras, for instance, you just put a Q in front of dense and pass the quantization function that you want to use. So really, really simple. They train a little bit longer, but the benefit on chip is obviously enormous. Now, you can also choose exactly which precision you want to use. Do you want to use bit width of 6? Do you want to use bit width of 21? That's a lot of choices. Some layers you can quantize a lot, some you can quantize little. So we've also added automatic quantization to the loop that scans which precision is best for each layer. Here's for a convolutional layer. You look at the model accuracy in an automatic scan, a Bayesian optimization, versus the bit size, and you find the Pareto frontiers, the most accurate and smallest models in an automatic framework. And here you can see the result of quantization-aware training. Here is the accuracy if you just put the numbers in buckets post-training, and here is what you get doing quantization-aware training, where you can maintain accuracy down to 6 bits, and the resource usage falls down dramatically. Quickly wanted to mention pruning, which most of you are also familiar with, and I guess most of you use it for your algorithms as well. Pruning consists of removing insignificant weights and synapses, basically setting them to 0. So that every multiplication by 0 is completely removed on hardware, so you can save a lot of resources. The way in which that works is that you usually add some level 1 regularization, then you do one iteration, you trim away the smallest weights, you repeat the iteration the second time up until you've reached some target sparsity of maybe you remove 90% of the weights. With pruning, that's a big research topic in its own field, by the way. So what we often see with pruning for large language models or image identification is that they're not very robust. So if you take your original image and you add noise to it, the accuracy drops down significantly. So here, as a function of the sparsity, here you've removed 50% of the weights. If you add, for instance, impulse noise, you've already dropped a lot in accuracy. And also here you can see the accuracy here in blue for an unpruned model, in orange where you've removed 90% of the weights. So do you always lose robustness and accuracy if you prune the models? It's actually not the case. It's a lot of interesting research showing something called the lottery ticket hypothesis. Look how happy this guy is. He found his lottery ticket. You over-parameterize your neural network, and then you prune with a clever algorithm. Here you can see the accuracy versus the percentage of weights that's been removed for a convolutional network. In black is the baseline accuracy. In blue is after pruning, removing 90% of the weights. You can find some winning ticket inside your network, which is far more accurate than the baseline model. You can also see the same for robustness. You distort the image, and then you look at the accuracy. So it seems that you can use pruning. It is also the same thing for ResNet. So you can use pruning to find a winning model inside your architecture, and which pruning method depends on what your problem is. So this is quite cool. Last shout out to boosted decision trees. We're so kind of consumed by transformers and diffusion models, we've sometimes stopped thinking about our data and does it really need fancy architectures. There's been a lot of hype around these papers. Why do tree-based models still outperform deep learning on typical tabular data? Neural networks are, in fact, decision trees. If you have tabular data, start out with a decision tree. No one is going to laugh at you. And it has a lot of benefits. So you can get the same accuracy. Here's for a quantized deep neural net and a BDT on an example task. Much, much faster to compute using much less of the resources. And I know it's heavily used in ranking systems for big companies. So this is nothing to be shied away from. And we're also working at a streamlined flow of creating really hardware-optimized decision trees and putting them on an FPGA also together with Google. One more thing, we want small models, and you can also get small models if you're more clever with your data. Don't read all of these things. So what you can see is that if you have very, very high quality data, 7 bytes of data compared to these enormous amounts here, you can really get almost the same. This network here is trained with small data, and it's a smaller model. You can get almost the same accuracy as when training on a lot of not high quality data. So that's also a trend that we're seeing in efficient machine learning is smaller models, high quality data.
I believe we had a question here, right?
Oh. Okay. So now I wanted to go quickly through, I actually wanted to kind of end the efficient compute sort of tools we're using here and really show how we're using some of these tools in this FPGA system. Every single one of these stickers represent the point we're putting machine learning for high luminosity LHC. So it will be everywhere in our detector. One thing we're going to do is that we got this encoded data out, so we have this sensor back in the level 1 triggers. But what we actually just have is basically energy cells in some space. We have no clue what that is. It's just sensor hits. This is just a big mess. So what we want to do is cluster all of these hits into disentangled showers from disentangled particles. And for that, we're using graph neural networks on FPGAs, where we're clustering together all of these energy deposits to be able to fully distinguish different particles that generates them. And we can do this in 3.5 microseconds. And in HLS4ML, we can really support specific graph neural network layers, but we want to move on to more support for PyTorch geometric, so lower level building blocks. Now, my favorite, unsupervised, self-supervised training. Most of our data is data, basically. It's unlabeled. What can we do to train when we have no labels in a completely data-driven way? So we talked about detecting new physics before, and we've been looking for new physics since we started taking data at the Large Hadron Collider. All of these plots show us looking for some new particle and excluding it. We didn't find it. So we've done hundreds, almost thousands of searches for new particles, and we haven't seen a single thing. So you might start thinking that we are maybe looking for new physics in the wrong way. So I said in the very beginning that the level 1 trigger selects which data is interesting or not. How do we select which data is interesting and which data is not interesting? The way we do that is that we always assume that the standard model is true and we have some alternative hypothesis. Then we say this region is not interesting, this region is interesting. Now that's completely fine when you know what you're looking for. We knew we were looking for the Higgs boson, so we know this is an interesting region and this is not an interesting region. But now we have nothing to guide us anymore. All of these new theories, quantum dimensions, supersymmetry, hidden dimensions, all of them are as valid as the others. We have to be a little bit more generic. We can't always assume a signal hypothesis. So you can imagine that the thing we usually do is that we look at energy of particles and we say high energy particles are interesting, low energy particles not. But you could also imagine that new physics, new particles hide down here where we actually threw them away in the event selection system. So in the level 1 hardware trigger, we already reject more than 99% of the events. Can we select events in a better way? So what we want to do there is rather look at the data itself rather than defining what's interesting a priori, and try to kind of classify them as being normal data or anomalous data. And obvious for all of you, then it's clear that you want to do outlier detection. And that's what we want to look at now as well. So we want to train autoencoders unsupervised on the data to compress, then reconstruct it again. This is often used in financial fraud detection, where you have a lot of normal events and very few abnormal events. For the bulk of the events, it can do this very well. But if you get an outlier, you won't be able to reconstruct the event from that smaller degree of information. And the difference between the two defines a degree of abnormality. And we now rather want to use that to select events where we throw away things that are normal and keep everything that's abnormal. And we want to do that in 50 nanoseconds. And we can do that in 50 nanoseconds. It's actually running right now at the LHC. All right, so we've selected our abnormal events. Now, why are they abnormal? What made them? Another thing we're looking at is using contrastive learning to really try to cluster events in space. So we look at the embedded space, and we want similar events to land different spaces in the latent space. So contrastive learning is basically a technique of self-supervisedly learn how to cluster events that are similar. The way you do that is that you augment your data. This is the real data. Then you do some augmentation of that data, making a pair. Then you define a similarity measure, like the cosine similarity between the two, where you expect positive pairs to be close together in some embedded space. And then you can use that similarity measure in a triplet loss to really figure out which pairs should be close to each other and which are different from each other. So you have a similarity loss between the pair that you created over all of the pairs of the full batch. All right. We also are looking at doing continual learning. So one thing that's kind of, yeah.
I wanted to ask about contrastive learning. So if you're in image space, these augmentations have kind of physical intuitions, or like we can design them, right? But if you're in some high-dimensional latent space from your sensor, like how do you design these augmentations?
You really have to know your physics data well. We know there are some rotations you can do. In the end, they're all vectors. So there are some vector rotations we can do that we know are basically kosher. Like we know, for instance, if we add a mirror of this event, turn it around, it should be the same event, but rotated. But there, like it requires a lot of domain knowledge to know exactly what's okay to do and what's not okay to do. It's a difficult task. Yeah.
Okay. So you only have 50 nanoseconds, right, to make something. So the network has to be really, really small, right?
Yeah.
So how many iterations can you have in this 50 nanoseconds? You know, like, if you have 2 layers, you might already have like 5 iterations, right? Or I don't know.
Yeah. I mean, that's, for now, the network we have is really small and already consuming the full 50 nanoseconds. So what I'm kind of thinking for this is that this is something, you select the data with a vanilla autoencoder, and then you can use it offline when you have time to analyze the data you actually selected. Then you add clustering on top, and then you can really analyze it.
Okay.
So in real time, it's very limited.
Do you know how many iterations? Or
No.
Okay.
So the continual learning itself is offline.
For now, it's being explored offline. Yeah. But all we want is basically, we want to have something that you can understand, a latent space that pushes things apart, basically, that you can understand things from. So we only want the latent space as it is, with nice distance metrics, and then everything we do in terms of learning is then offline. Yeah. Okay, and then we're also looking into doing continual learning, because every time, for instance, the moon shifts its position, the accelerator moves. So there's misalignment. Every time there's a flood and water floods under the experiment itself, the detector shifts. And we have a lot of radiation. So the sensors are continuously bombarded by charged particles, meaning the sensor sensitivity changes a lot. If you want to do self-supervised learning, obviously, we know the sensors will change. So we have to figure out if we really have to train everything on all of the data again, or if we can train as the conditions change to gradually update the weights for the appropriate new conditions that we have. So we start out with transparent sensors, and if we have an algorithm that was trained with nice transparent sensor, at the end of the month, we maybe have blackened sensors. All right, and we're also inviting a lot of contributions from the community to help us do anomaly detection better. So we currently have a data challenge on real-time anomaly detection out, where you have a data set representative of what we have at the LHC. We have a tutorial on anomaly detection on FPGAs with HLS for ML, so please make a submission. We'd be happy to have some contributions from you. Okay. We're also not just doing LHC physics. We also work with, other experiments. So I don't know if you've seen these experiments. They try to detect neutrinos from out of space. They're located deep on the seabed to detect light. They're called Cherenkov detectors, and you have hundreds of them basically chained to the floor. And the reason they're deep underground is to get rid of background, basically. Because every time you have a signal, you have to send all of that data to shore. And one of their biggest backgrounds in this experiment is fish swimming by. Bioluminescence from fish can generate bursts of up to a few megahertz. So that means every time a fish swims by, you're transporting all of this data to shore, which you don't want to do. So what we're working on there is to have a machine learning-based, FPGA-based trigger located on the seabed that can figure out if this was a signal or a background event before sending the data to shore. All right. Then we go to the infinite time domain, the high-level trigger, where we have roughly like autonomous vehicle time to make decisions, 300 to 400 milliseconds. This system used to be CPU-based, 30,000 cores, and it would do a bunch of things, like get the raw data in, do tracking, and then do the full event reconstruction. And since we are now approaching this domain where we have a lot of data, we're currently offloading the most resource-intensive computations to a GPU, which increases our throughput by a factor of 2 and can reduce our power consumption by a factor of 30. So for instance, you have raw data coming in, you transport it over to the GPU, it does some tasks that are faster on a GPU and then transports them back. And in the future, we want to do 50 to 80% of our compute on these accelerators. One of the things we're most interested in doing is doing this full reconstruction, combining information from all of these different parts of the detector. And we can't do it on all of the collisions, only 17%, because our bandwidth is limited basically by rate and event size. So we really can't run this complicated process on all of the events. So what we're currently doing is looking at graph neural networks as fast approximations of doing this full event reconstruction. And here you can see an example of a classical algorithm that we've been using up until this point, and the graph neural network equivalent, and you can see it does quite a good job. Now the benefits of this is that this lives natively on a GPU, so we can just add another IP after this and run everything on a GPU, freeing up the CPU for other tasks. So we're currently looking into a lot of machine learning, fast approximation of classical algorithms. AI engines is also something that's really interested to us for multiple parts of the real-time processing. So there's a lot of processors on the market that we want to investigate for CERN purposes. So this is the Xilinx Versal AI processors. It has 400 AI processors and basically FPGA fabric. And the data can move as it wishes back and forth between the processors and the FPGA. And we're also looking at using these as we get more and more machine learning algorithms in the level 1 trigger. All right. We saw this plot before also, where I said, oh, we're going to need so much more compute in the future. And then I mentioned total CPU. We didn't really talk about FPGAs, how much more of work it would be for the FPGAs. And most of the compute we're going to need in the future is to do simulations, to produce simulations. It takes 60% of all of our CPU to generate these simulated data, which is kind of crazy. If you look at this cake diagram here, you can see the green, the orange, the pink, and the brown. All of this is basically generating simulated data. It's not even processing the real data, those million cells. So we use a lot of compute on simulation. And like I said, we have to simulate everything from the very, very small to the very, very big. The way we do that is in 3 steps. We do one very low-level simulations where we collide protons together and they let them decay into a handful of particles. Then we simulate the full detector response, which is really, really hard and really, really slow. Then we run our full reconstruction software on that detector information, which is also very, very hard and very, very slow. What we want to do is basically replace this step and also this step at some point with machine learning algorithms. So here we're talking about generative models. So we usually use a library called GANT4 to produce our simulated events, which is really, really slow but highly accurate, as I mentioned before. Now we want to try to rather generate a fraction of those events and then train a surrogate like a GAN, a VIE, a normalizing flow, a diffusion model to get the same amount of events out. So something fast but also accurate. Now what's really, really different in particle physics with respect to other fields is that we need really high fidelity simulation. If your picture of a cat is a little bit off, it doesn't matter, but we are really looking at very, very kind of outlier distributions. So we need to model this very, very well. So one of the biggest hits in particle physics is doing diffusion models to generate our simulations, where you basically learn how to add Gaussian noise to an image until you get basically just noise out. And if you can do that, you can also reverse the process. So from noise, gradually remove noise until you get the original image back. This is something we're also interested in doing for simulation. So here you can see an example of what diffusion can do for particle physics. So wrapping up, in our fast machine learning community, we do a lot of other things too. So we work with Volvo company, Sensact, on semantic segmentation for self-driving cars. We make chip implants for predicting epileptic seizures. We also work on neural network accelerators for controlling quantum computer systems, for fusion, for this one is food contamination detection. And we also benchmark our algorithms in big competitions like TinyML and MLPerf, if some of you know it. If not, I'm just going to skip over it. It's for those who care. And I hope that's inspired you to join our fast machine learning lab community. So please, we'd meet every month to talk about real-time AI, efficient machine learning, etc. It's been a pleasure to have you ask me questions and listen to me. Thanks a lot.
Thank you very much, Thea, for this great talk. I must admit that you made most of these like really intricate ideas very easy to understand and grasp, and also your slides were great. I mean, very colorful, so attention grasping.
Great to
so
hear.
thank you for that. And because we have only a few minutes before, I mean, we can go ahead, but we have paused the session waiting. Let's skip to the Q&A part, because I believe we have some questions.
So you mentioned that decision trees should be fine for tabular data. And I was wondering, do you know of applications on how to do things beyond classification regression? So for example, dimensionality reduction or style transfer with decision trees. Is this something that exists?
I mean, we are using it now for anomaly detection or looking into isolation forests for anomaly detection. But at CERN, it's mostly really used for classification or for regression. Yeah, but isolation forest is also something we're looking at. Otherwise, if someone is also looking at it for other purposes, let me know.
So when you embed symmetries into these neural network architectures, normally you do it by constraining the number of trainable parameters. You impose some constraints and you reduce the number of trainable parameters.
Yeah.
And in some experiments that I have done, whenever the resources or the number of parameters are actually quite low, as I expect you guys are working on, then the model is quite difficult to train. At some point, you lose expressivity versus imposing the true symmetries that you know from the system, but also they are a little bit challenging to train.
Yeah.
I was wondering if you guys have faced something related to this, and if you have some experience in this aspect.
No, I think it's really kind of stupid things, a bit like kind of fine tuning and weight initializations can even matter for these sort of things. So it's been really hard to get something that's also robust. But we don't really have a technique to reduce this, unfortunately. But we see a lot of the same also.
Perfect, thank you.
Not perfect. We should.
No. And I wanted to say outstanding presentation.
Great to hear.
I have another question here. Regarding the pruning network optimization part, I was wondering if is there any hardware that is optimized for sparse multiplication in order to have benefits of this sparsity that you gain with pruning?
Yeah, I mean, for us, FPGAs are a little bit there, whereas every time you have a single multiplication with a 0, it's just removed and not done. But yeah, that doesn't apply to everything. But for FPGAs, we can really harness even sparse pruning, which you can't on GPU, for instance. Yeah.
Thank you.
And then, I mean, you can do like the basic like filter pruning kind of stuff too. Yeah.
Thank you.
I have a question about the quantization of the weights of the neural network. I've seen that now the quantization is 4 bits, but there are a few papers about binary neural networks, and the advantage is that you just use XNORs instead of multiplications. And my question is, was this never tried for this task?
We have specific implementations for binary and ternary nets as well, so you can also do that. It depends on the task that you want to do, and also for us, we don't really need to go binary. And we often are completely fine with 4-bit precision, but with HLS for ML or QKeras, you can use binary and ternary networks as well, with dedicated FPGA implementations of those operations. So they're tried and they're in there, and you can use them at will.
Okay, thank you.
I also have a question about quantization. I was wondering how hard it is for you to quantize networks, in the sense that when you're quantizing, you're losing performance. So what is your threshold?
It's really, we see that we don't, basically. For the tasks we have, if we use quantization or training, for a lot of tasks, we can retain the same accuracy down to very low bit widths. So we don't even lose performance with quantization or training.
Okay.
We pay in training time because it takes longer, but accuracy after, we have not been made to sacrifice yet.
Right, that's
yeah.
impressive.
It's cool.
So it seems that going with electronics below, say, tens of nanoseconds will be hard even in the future. So do you see some other platforms, I don't know, maybe optical ones, or some other things that might work faster?
I'm not sure about faster. For us, I mean, ASICs has the speed we already need. I don't know if there's also speed benefits to neuromorphic chips or if it's only power. In terms of latency, I don't know. I don't know. But we have looked into lower power solutions like, yeah, neuromorphic chips, spiking neural networks, but only for power consumption, not for latency.
Thanks.
But usually if you're clever where you put exactly where you place and route every single operation on an ASIC, we have, like you saw for the BDT, 5 nanosecond latency on an FPGA. So it's well within the constraints we have. And you can still drive the FPGAs way faster than what we're currently doing.
Okay, and because we are waiting for poster session, we have to unfortunately cut our Q&A shortly. But
please
you
ask
can,
me afterwards.
of course,
I'm
you
here.
can catch Thea after. So again, please a round of applause for our speaker.
Thanks a lot.